Alrighty, welcome back to Fun Maths. Today we're looking at rules for differentiation. I think there's a fair bit to cover actually today, so let's get stuck straight into it. In particular, this exercise, when we're going to be looking at calculating derivative, we're looking at x to the power of n, where this n is a positive power, so it could be 1, 2, 3, etc., etc. We'll talk about how to deal with negative numbers a bit later down the track. So it says here, from your work in the first section of this, so previously you may have noticed from first principles the following types of things. If you had a function of x being equal to x, the derivative, or f dash x, of this was 1. Likewise here, if you had x squared, the derivative, or f dash x, was 2x. If you had x cubed, the derivative was 3x squared. Now, some of you may have discovered a little bit of a pattern here or seen what's happened. Essentially, there is a rule that we can follow. If you have a function of x and it's to the x to the power of n, if you're going to calculate the derivative, or f dash x, of that, what happens is this power of n comes down the front, and then we subtract 1 from the power. So for example here with x squared, obviously the 2 comes down the front, gets multiplied by this 1 that's at the front, so 2, and then we take away 1 from the power. Taking away 1 from 2 becomes x to the power of 1. We don't write x to the power of 1, we know it's just x. Yeah. Likewise here, if you've got x to the power of 3, following this rule, the 3 comes down the front, gets multiplied by what's in front, which is the 1. Then we take away 1 from the power. 3 take away 1 is 2. Now some of you might be going, oh, okay, well what happens here with x to the power of 1 becoming 1? If you think about it for a little bit, if you've got x to the power of 1, we don't normally write that. The 1 comes down the front, and then we take away 1 from the power. So with the 1 out the front, you'd end up with 1 lot of x, and then you would take away 1 from this power. 1 take away 1 is 0. X to the power of 0 is just 1. So you end up with 1 times 1, which is just the 1 there. Alrighty, the good news is there's a nice big theorem to prove that. If you are happy to look through that, you can do that in your own time. What we need to look at in particular, first of all, is how we handle certain different aspects of this derivative functions. So, it says here the derivative of a polynomial function. There's certain types of things that we need to do. If you've got a constant function, such as f of x as being a whole number, so just a number by itself, it might be 2 for example, then the derivative f dash x of a constant number is going to be equal to 0. Cool. If you have a linear function, mx plus c, the derivative of that is just going to be the m value. Where you have cases as follows, f of x is equal to k times g of x. It says where k is a constant that can be pulled out the front of this other function, then what happens is the derivative f dash x is going to be that constant value pulled out the front and then multiplied by the derivative of g here, so g dash x. An example of that, to hopefully make it a little bit clearer, let's say you've got the function 5x squared. That's really that k value here, the constant value, multiplied by this other function here, which we'd call g of x. To work out the derivative of this, f dash x, that constant comes out the front, and then you are differentiating this g of x function. In this case, the 2 comes down the front, we take away 1 from the power, it's 2x. From here, we can then multiply that out. 5 times 2x gives you the 10x there. Next part, sum. If it's saying here, if you have a function that's made up of smaller functions, you just work out the derivative of each of those parts. So let's say you got g of x plus h of x, then the derivative of f of x is the derivative of this part plus the derivative of this part, so forth and so forth. Same thing applies for the difference if you are taking them away. So yeah, just really quickly, if you had x squared plus 2x, you'd work out the derivative of the x squared part, which is 2x, then you'd add on the derivative of 2x, which is 2. Cool. Important thing to know is the process of finding the derivative function is called differentiation. Perfect. Alright, let's have a look at some examples of doing this. It says here, find the derivative of x to the power of 5 take away 2x cubed plus 2. And another way of saying this is differentiate this function with respect to x. It's just both of those ways they might say it. It's just saying, hey, calculate the derivative. So, as we said before, we're just going to work out the derivative of each of these parts separately and go together there. So, we've written out f of x, check. We're then going to work out f dash x, or the derivative. So, working out the derivative of this x to the power of 5, remember the 5 comes down the front, which is really being multiplied by the 1 here, which is 5. We then take away 1 from the power, it's x to the power of 4. Check. Next, we've got this one here, negative 2x cubed. Work out the derivative of this. Really what's going to happen is the 3 gets multiplied by the negative 2, which is negative 6, and we take away 1 from the power, which is 2. And you can jump sort of straight to that part there when you get the hang of it a little bit quicker. Or, if you're using the rule above where you've got the constant, we know that negative 2 is the constant. We differentiate this here, the x cubed. 3 comes down the front, take away 1 from the power. It's 3x squared. And then you can do the multiplication later on. It's up to you how you go about doing that. Last but not least, we've got this positive 2 here. It's asking us to differentiate that part. We said above from the rules that if you have a constant value, then the derivative of just a constant value becomes the 0. So you don't even need to write it out over here. Perfect. Move on to the next question. We've got another function. It's asking us to find f dash of 1. So what we're going to be doing is, first of all, we need to find out the derivative, and then this is saying substitute 1 into the derivative to evaluate that. So first part is to calculate the derivative. So we've got 3x cubed. We multiply the 3 by the number in the front, which is 9, and we take away 1 from the power, which is 2. We've got 9x squared. Next, we've got negative 6x squared. We multiply this 2 by the value at the front, which is negative 12. Take away 1 from the power, it's negative 12 x to the power of 1. This constant 1 here, the derivative of a constant is 0. You don't even need to write it out here. So we've got the derivative f dash x is 9x squared, take away 12x. Second part of this question was saying, hey, find out what happens when we put 1 into the derivative. We can do that by putting a 1 where the x is. 9 times 1 to the squared is 9. Take away 12 times 1, which is just negative 12 there. 9 take away 12 is negative 3. Happy days. We should be able to move on to the next question. A little bit later down the track, they can ask you to do things like finding the gradient of a tangent line. And so we've done this type of stuff before. The good news is we can now calculate the derivative and apply a process there for that. So it says for worked example number 9, for the curve determined by the rule, they've listed it here, it says find the gradient of the tangent line to the curve at this particular point. Alrighty, so what we're going to do is we're going to find out the derivative of the function, so f dashed x. So doing that, 3 times 3 is 9, x, take away 1 from the power, so it's 9x squared. 2 times negative 6 is negative 12, take away 1 from the power, so it's just x to the power of 1, which we don't even write the 1, we just write x, so we've got negative 12x. This constant just becomes 0. We don't even need to write it out. We've got the derivative here. Next, what we're going to do is find out what the gradient is at this particular point on the graph. And so what we're going to do, we're going to substitute in the x value into the derivative to find out what's going on. Okay, so substituting in at the point x equals 1 into the derivative will tell us what the gradient is at that particular point. So substituting in 1 into the derivative, where we see x here, we're going to plug in the 1, we get negative 3. So what you can say is at this particular point, whoops, the gradient of the tangent line at that point to this particular function is going to be negative 3. Alrighty, there are some different alternate ways to write out derivatives and things like that. And one of them again is Leibniz's notation. And so let's say you had, rather than using f of x and f dashed x and things like that, you could just have a function written as y equals x cubed. Then what you could say is that, or they could ask is, hey, what's the derivative? And what they would write it is as is dy dx. Okay, and we had a bit of a chat about this in a previous video. So if you are asked to work out dy dx, then you are just being asked to calculate the derivative of this here. So you'd write out dy dx is, obviously the 3 gets multiplied by the 1, so it would be 3x squared, take away 1 from the power there. Perfect. Alrighty. Worked example 10, it says here, we've got some some functions, y equals t squared. In this particular case, or some equations, they're asking us to calculate dy dt. Okay, that's just asking us to work out the derivative of this. So like we've been doing before, yeah, it's just different notation. You can write out dy dt, which is the derivative, is the 2 gets multiplied by the 1 out the front, which is 2, and we take away 1 from the power. So it's t to the power of 1, which we don't need to write. It's just 2t. Here, same difference. It's asking us to calculate the derivative of this here. And remember, we need to work out the derivative of each of these parts and sum them together. Dx dt is equal to, the 3 comes down the front, gets multiplied by 1, so it's a 3. We take away 1 from the power, becomes 2. We've got t here by itself. Remember what we spoke about, it's just the value that's in front of this here, which is just 1. Yep. So it's really t to the power of 1 gets multiplied by the 1, which is 1. Take away 1 from the power, which is 0. T to the power of 0 is just 1. You'll get the hang of that one. Oops. This one here, cool, a fraction, no need to panic, we just still do the same process, yep. We're calculating the derivative dz dx, so we multiply the value out the front by the power, so 3 times a third is 1, and we take away 1 from the power, which will be 2, so it's 1 lot of x squared, which you don't need to write the 1 there. X to the power of 2 is the 2 comes in the front, and we take away 1 from the power, adding on 2x there. Cool. These ones here. There's an extra little step to do with these before we can differentiate. What we need to do with each of these is sort of expand them out before we can do that differentiation process. So we've got x plus 3 squared. What you would do is you'd write it out in expanded form, and then once it's in expanded form we can apply the differentiation process as usual. Here, same difference again, you'd have to expand this out and expand this out. In full, group the like terms. Once it's all expanded out, differentiate as we've been speaking before. This one here, it's, we first need to simplify things down by simplifying each of these things down, cancelling out this x here and this x here. X fits into itself once here, and also fits in up here, and that cancels out with that one there. Once we've done the cancelling out, we can differentiate. This one here, again, pretty straightforward. 3 times 2 is the 6. Take away 1 from the power is 2. So we've got 6x squared. if you've got a constant value on the end, whether it's positive or negative, the derivative is going to be 0. So you don't need to write plus 0 on there. You can just leave it blank. Alrighty. Oh, another form of notation that they can use is they could say find the derivative of 2x squared, take away 4x with respect to x. That could be written as find d dx of that there, which is just asking you to find the derivative. If they're asking you to find the derivative of a function with respect to x, it's just the same as finding f dash x. Yep. These are just all different ways in notation that you can use to ask to be calculating the derivative. Alright, I believe that people should be fairly happy with those there. Alrighty, this is the last one I want to have a chat about today. It says for each of the following curves, find the coordinates of the points on the curve at which the gradient of the tangent line at the point has the given value. Alrighty, so we've got y equals x cubed, and it wants to know at what point is the gradient equal to 8. So what we need to do for each of these is work out the derivative and then make the derivative equal to the gradient, and then we'll be able to go back and find out at what point it was that these gradients existed. So this one here, we've got x cubed. We need to work out the derivative of that. 3 gets multiplied by the 1, take away 1 from the power. It's going to be 3x squared is the derivative. The next part is if you've got the derivative, which is the gradient function, then we know the gradient was equal to 8. So we're going to make the derivative equal to 8, which we've done here. From here, it's a matter of solving to find out where x, what the value of x is. So obviously you'd need to divide this side by 3, divide this side by 3, take the square root of both sides. Remember, when we're taking the square root, it can be the positive and negative values of both of those. Now, some people might be a little bit confused how we went from both positive and negative square root of 8 over 3 to this here. You have to remember your surds. We know that the square root of 8 is the same as square root of 4 times 2. When we simplify down that surd, that's the same as the square root of 4 multiplied by the square root of 2. Square root of 4 is just 2. Yep, so you end up with 2 square root 2 over the square root of 3. And what they've done here is just rationalize the denominator by multiplying by root 3 over 3. And by doing that, you end up with just the 3 on the bottom line. And here you've got root 2 multiplied by root 3, which is obviously the root 6 part, 2 root 6. So that's just a recap of how they got to there. Now, once you have found out the values of x that allow for this gradient, we can plug this value back into the original equation to find out its corresponding y coordinate. So plugging positive 2 root 6 over 3 back into x cubed, we get its corresponding y coordinate. In this case, we also need to do the same for negative 2 root 6 over 3. Plug that into the original equation and you'd get its corresponding y coordinate. And that says that at these particular points, these 2 points, the gradient is 8 for this function at that particular point. Last two, again, work out the derivative, which they've done. Make the derivative equal to the gradient that they've specified here. And we can rearrange things and work out what the value of x is here and solve that. So this is saying at x equals 2, the gradient is 0. They want to know what the coordinates are, so you need to plug this x equals 2 back into the original equation to find its corresponding y coordinate, which in this case is negative 2. Last one here, we've got y equals 4 take away x cubed. Again, we need to differentiate this and make the derivative equal to negative 6. Here is the derivative which we've worked out, making it equal to negative 6. It's a matter of simplifying things down. Divide this side by -3, divide this side by -3, and then take the square root of both sides, remembering that it can be both the positive and negative value of that. So we know it's happening at both positive square root 2 and negative square root 2. Remember, square root of 2 is the same as 2 to the power of a half. So 2 to the power of a half, we can plug back into the original equation and get its corresponding y value, and also the negative version of that. Thank you for listening up. It's been a long one today, but well worth it. Bye for now.